My next presentation is, as was mentioned, remarks on searches for interstellar meteors. And I will disappoint you, but I will not actually discuss anything about the real interstellar meteors. I will focus on the database assessment, or to be more precise, I will offer a few remarks and few graphs for you to have some kind of so you can imagine how the situation looks like. So I will mainly talk about shower meteors with hyperbolic orbits, because this is the easy way how you can look at the database and see what kind of errors you are actually working with without actually seeing the errors. And the other part will be about Kresaks diagram, which is a useful way to visualize the database. So just a quick overview. There are many databases freely accessible. And if you look at them, about 10%, not in all of the databases, but in many of them, about 10% of the orbits are hyperbolic meteors, which might indicate interstellar meteors, but in many cases, this is just the result of errors. So if you want to search for interstellar meteors, you need to look at the errors. You need error propagation, not only for the meteors you are investigating, but also for the whole database. You need to see the whole database to see if you actually have anything to work with, if it is worth it, to be honest. So let's imagine that we take a hyperbolic population from some database, and we do not use error propagation. We assume that we are working with interstellar population. And there is quite a simple way how to calculate point of origin for hyperbolic meteoroids with simple celestial mechanics, which I'm not going to get into. And you can make a pretty nice graph like this, visualize it in the ecliptical coordinates. This is a 2D histogram, so you can see the groups of meteoroids. And this is not a real interstellar population. These groups, you can see it, are actually shower meteors, which got here because of the errors of the measurement. And even more prettiest way to visualize it is if you calculate the space density of each meteor based on the similarity of the orbits. And you can clearly see now the groups of shower meteoroids, shower meteors or stream meteorites. If you want further convincing that these are shower meteors, you can easily just visualize it based on the solar longitude and the geocentric velocity. There is no problem to now associate it with the known meteor showers. And the thing is that you can assume there will be some hyperbolic meteoroids among the stream particles, but definitely not in this huge amount. So this is clearly work of errors, this huge spreads about the parabolic limit. Now let's look at the Kresaks diagram, because it's a very useful way to visualize the whole database. So we are visualizing the geocentric velocity of the meteors and the elongation angle, which you can calculate from the geocentric velocity vector of the meteor and the heliocentric velocity of the Earth. And in this elongation angle is actually the information about the radiance of the meteor, about the declination and the right ascension. Now, this graph is created for the selection of Edmond orbits from around the 1st of January. So you can clearly see the red line, which is the parabolic limit. Everything about this line is hyperbolic. And Edmond is actually one of the databases which incorporated quality filters. To filter out the bad orbits, the inaccurate orbits, but we are still left with about 6% of the hyperbolic meteors, and this includes shower meteors. On the right, you can see the black dots. Those are sporadic meteors, and the green ones, which are shower meteors. And you can see there is clear spread, clear continuous spread about the parabolic limit, which you shouldn't exist, and it's bigger and bigger when you look at the higher and higher geocentric velocities. You can actually visualize the same data when you calculate the density in the phase space, as we have seen before.
We have 3 more minutes.
Okay, thank you. So you can see the groups which are actually the shower meteors, and it shouldn't spread about the parabolic limit as much as it does. Now it's a little bit hard to imagine how the right ascension at the declination changes when the elongation changes. So I prepared a few GIFs. On the left side, we have a GIF for fixed declination at 50 degrees, and the right ascension, which is changing, and the elongation is changing with it. This is for the simulated data for January the 1st. On the right side, we can see the stacked pictures. And if we were to calculate it for the range of declination from minus 90 to 90 degrees, we can actually see how it looks on in the sky. The red space here, those are all the points when we can expect hyperbolic meteors. And what it looks like when we look at the reality. This is again the Edmond data, the selection around the January the 1st, and we can see that with the increasing geocentric velocity, just like on the right side, the population is sticking together. Even the few hyperbolic meteors we actually have there stick to the elliptical orbits, the black ones. There is really no spread in this region where we could expect the hyperbolic meteors. So we can say that there are probably no real hyperbolic nor interstellar meteor in this database. If any, then very few which are probably of solar system origin. So the conclusion of this, or my message to you, is please always assess the database. Even if you do not have errors, you can look at the graph and you can see what you are actually working with before you start searching for interstellar meteors. So thank you.